Okay, so hello everyone. We'll now continue from where we had left off in the last class. In the last class, we were able to find the values of normal strains and the shear strains. So this and this in terms of the displacement. So this is something which we had done in the last class, and we'll continue this topic further ahead. So okay. Now, after having derived this shear strain gamma x phi, and which I had told you in the last class how the angles are calculated, we have to make the following comment uh, from the textbook, that not all the relative displacement however involves deformation. Some of it arises from rigid body rotation. Now, as you see that all the points around here are displacing, but that does not mean every displacement will actually contribute to deformation, meaning it may not necessarily contribute to these strains terms which we have calculated, right? And I mean, there is a possibility that the strains are all zero. Okay. Now, some of these terms actually arise from the rigid body rotation, and for a small derivative, the rotation about the x-axis, about the z-axis, sorry, which is the thickness direction of the line OC. So consider the line OC. Okay. So you can write omega. Let me just remove this there. So rub off this so that there's space over here, and yeah, let's just. So there's a recording for the previous lecture anyways, if you need to go back and see how this has come up. Okay. So what we had derived was that epsilon x is equal to dou u by dou x, epsilon y is equal to dou v by dou y, comma xy is equal to dou v by dou y, sorry, dou v by dou x. Yes, dou u. Okay, so this is where we had come, and for small displacement derivatives, meaning these derivatives which you take, they are always small. The rotation about the z-axis of the line OC, this is the line OC, omega of z of the line OC is written as v plus dou v by dou x into delta x minus v into delta x, and this turns out to be dou v by dou x. Okay, so v plus dou v by dou x into delta x is the minus v divided by delta x is the rotation. So you see how this value has come up. Okay, this is the term which we are referring to over here. Okay, so this is the so-called final length of this part, and v was the original length. Okay, over here, and for the segment OC is how you have taken this. Okay. Okay, so that's how you have defined the rotation component, and similarly for the line OE, you should be able to write this as a minus of u plus dou u by dou y delta y minus u, sorry, plus u divided by delta y equal to dou u by dou y. Okay. Now, can you think of a reason why you should have a minus over here, a plus over here, and a minus over here, and a plus over here? Can you think of a reason why that should be true? you'll have to think of a way why the rotation is calculated in this particular form. Okay, so you can start with OC, that's always the easiest, and you should try to question yourself why these terms are written in this form, why there's a minus, why there's a plus, and so on. Okay, but eventually you would get the omega z of OC as a dou V by dou X and omega z of OE as dou U by dou Y. These are the so-called rotation about the z-axis of this line, and for this point O you must write out sort of an average value, and that would be omega z is equal to half of omega z OE plus omega z OC. This is equal to half of dou V by dou X minus dou U by dou Y. I think there should be a minus term over here. Yes, there will be a minus term, so you can make that correction in your book. Okay, so that's how you have arrived at this, and the questions which I have asked you, those are something which you must think about. Okay, so the strain components you have already defined, here they are. Okay, and they have been defined it in this form. Now the equation 4.33, this is 4.33, indicates that the strain components depend linearly on the derivatives of the displacement components. I mean, by looking at this equation, it is very clear that the derivatives of the displacement are linearly related to the strains, and they are all valid under the assumptions of small displacement derivatives compared to unity. So all the derivatives which you see everywhere, they are all individually small compared to 1. Okay, only then you can sort of, I mean, if you recall this particular term, it is actually truncated term, right? So there are higher order terms after this. So that has happened, though you could ignore them only because the derivatives were very small compared to 1. Okay, so this is a small strain, and then you have the small rotations over here which you have calculated. This is the average value of rotation, and the derivation has I mean, you have seen the geometric meaning of this particular term. Now you have considered this, the deformation of this element in 4.29 in the limit as the size of the element shrinks to 0. Thus, we consider the strain components to define the deformation at the point O. So this is the whole point. Just like in the stress case, even though you are utilizing the knowledge of this extension and the rotation of, say, this and this element, you say that all of these things are actually valid at the point O because of the shrinking and infinitely small dimension of this square which you see OCDE. Okay, so that is what is written in your textbook, that thus we consider the strain components to define the deformation at the point O. So we therefore speak of the plane strain at a given point in a two-dimensional body as given by the strain components Ex, gamma xy, gamma yx, Ey. Okay, this is the strain components over here, and we say that gamma yx is the same as gamma xy. In your textbook it is written that you define it in this form, but in reality this comes out because of the geometry, meaning you have done the derivation of gamma xy and then you wanted to calculate this angle and then subtract 90 minus this particular angle. What you can do is you can repeat the same analysis for gamma yx Okay, so what would gamma yx be? And then you have to write those expressions, and from this geometry you will see that gamma yx is the same as gamma xy. Compare this to the stress, which was tau xy was equal to tau yx. The reason that was equal because the moments were balanced about the center. The reason the shear terms of the strain are equal or so-called symmetric because of the geometry. Okay, so the reasons of them being equal are very different. Okay, so one last note which we must make in this section is the fact that the deformation at points adjacent to point O will in general differ from the point O, meaning you have found the quantified the deformations at O using strains and rotation. The comment says that the adjacent points, say E and C, they will have their own separate and different strains and rotation. Okay, and you will do it in the same way. For example, C, you will have to now make something like this, and then this point and this point, so extension in this one, extension in this one, then the change in angle and so on. So the strain and rotation for C will be different than that of O. That's like generally true. Now the fact that two components of the displacement serve to define three components of strain indicates that the three components of strain cannot vary arbitrarily in a field of non-uniform strain. So this is the idea. There are two displacement components in this two-dimensional plane strain problem, u of xy and v of xy, and the strains which you have found out using them, okay, these are the relations, are actually three strains, okay, using these two displacements. And the idea is that the strains now cannot be arbitrarily varying in the field of a non-uniform strain. Okay, they must have some relations. These three strains must have some relation among themselves because they are linked to only these two displacement terms. Okay, so that relationship among strains is called the compatibility equations. Okay, and the whole point of this is that the strains cannot arbitrarily change according to their whim. Okay, they are related only by two displacement components. So the derivation of this is not done in a second year course like this one, but you should just be aware that you can, I mean, there are these compatibility relations over there. Okay, the existence of this compatibility equations is something which you should be aware of, and the motivation also as well. Okay, fine. So the last part is this indicial notation is not very hard. I mean, you want to write this ex. Okay, what you would do is you would just write e1 is equal to dou u1 x1. The second one you would write as dou u2 by dou x2. Okay, u2 is v, x2 is y, and similarly gamma 1 2 or gamma 2 1 will be equal to dou u2 by dou x1 plus dou u1 by dou x2. So that's how you can write the indicial notation, and you can write it in the index form as half into dou ui dou xj plus dou uj dou xi. Okay, so E11 is your epsilon 1, E22 is epsilon 2, E12 is actually half of gamma 12. Okay, so this is a convention, as I've said again. I mean, you don't have to use it a lot, but you must be aware because the advanced courses on this subject almost entirely use this convention. Okay, so we continue to move towards the next topic of deformation, but I hope you can take a moment to understand that all the theories of stress which we are learning right now are actually, and as I've said before, completely independent of the theories of stress. Okay, you can see some commonalities perhaps in the notations and perhaps in the symmetry of the shear terms, but all the reasonings and where they are coming from are entirely different. Okay, so that is something which you should pause and definitely understand and compare and go back to those derivations, check again, just to see and be able to appreciate this. Okay, so we now come to the section 4.11, which is strain components associated with arbitrary sets of axes. Okay, sounds similar, right? From the previous case. So we have, for example, Ex, Ey, gamma xy. These are the strain components in the Cartesian sort of system. Okay, Cartesian axis. Now, if you want the strains to be defined along any set of arbitrary axes, what would you do? And remember, the motivation of it is coming from the example I gave you about the bones or the wood, which has fibers along directions. And then I had told you that you want the stress to be found out along the fiber directions. What would that be? Similarly, in that exact very same problem, if you are expected to find the strain components along the fiber directions or away from the fiber directions, or for that matter in any arbitrary set of axes, how would you proceed? And that is something which we would want to do in this particular section. Okay, okay, we consider the situation which is shown in figure 4.30, in which the deformation of a small element is shown in terms of the displacement components u dash and v dash parallel to x dash and y dash set of axes. Okay, so the shaded part OHGF is your element, small element. Okay, you see the x dash axis and the y dash axis. So it has come out by a rotation of this angle theta, just like the case which we have studied about stress. Okay, and you would want to find the, you would be able to write the displacements in this primed system. Okay, so let's do that. So just like I'm in this equation 4.33, you can write Ex dash is equal to dou u star, dou u dash by dou x dash. Ey dash is equal to dou v dash by dou y dash, and gamma x dash y dash is equal to dou v dash by dou x dash. Okay, so this is true for the system which we have right now. Okay, I mean, this does not anyway refer to the original system which is x and y Cartesian axis. So this would be true for any, I mean, this element wouldn't even know that there is an x and y coordinate axis as well. Okay, so by this stage there is no problem. Now the next step is to inquire as to the nature of connections between the strains of this. So this is 4.37 and the strains of 4.33. So the strains of 4.33 for this figure would be in the xy coordinate system, and the 4.37 strains are in the x dash y dash coordinate system, and the objective is to be able to find what relationship exists between these two systems. Okay, And again, I mean, you have done the maths part of it in linear algebra. Okay, you have done the maths part of it again, coming from a different side in the theory of stress, and you will do the same again. Okay, right now, of course, with a visual and a physical understanding of what is happening, unlike the maths course which you have studied about rotation of tensors and things like that. Okay, we observe that since geometric compatibility requires u dash and v dash in figure 4.30 to be continuous functions of positions in the plane. Okay, remember, geometric compatibility meant that there were no voids or gaps or cracks and things like that. That would only happen when u dash and v dash are also continuous, just like, look at over here, u and v were continuous. We can express these displacement components either as functions of x dash and y dash or as functions of x and y. So, okay, so let's do that. So this equation, for example, can be written as equal to dou u dash dou x, okay, and dou x by dou x dash. Reason is u dash is a continuous function in x and y. Okay, similarly v dash is also a continuous function in x and y, so you can do this particular operation, and then this is half of dou u dash dou y by dou x dash. Okay, so that's how you would be able to write this term. Okay, now the same operation can be done in the second terms as well. So in your textbook you can please refer to equation 4.38. Okay, it has this breakup of ex dash ey dash and gamma x dash y dash. So you can see that particular part over there. Now if you look at figure 4.30, you can obtain the relations 4.39. So please check your book what relations 4.39 are, and I'll write one of them. X is equal to x dash cos theta minus y dash sine theta. Okay, so let's see how they can be written. So if you take any x, where can I take any x? Say you want to consider any point. Let me just write another diagram. Okay. This is the xy. So this particular point can be written as xy. Now you want to write this x in terms of x dash. Okay, so what would that value look like? So for this we must go to problem 1.2 also. Even there you can sort of solve this, but let's see if we can find an easier way over here. So it is problem 1.4, problem 1.2. okay, so it's in chapter 1. Let's check where that problem is. Yes, so if you go to problem 1.2, okay, there is a very easy transformation which is derived. So x dash y dash is equal to a transformation matrix and x comma y. So you may have learnt about direction cosines and things like that. So this is where that is coming from. So I would recommend you to please go back to problem 1.2 and be able to write this. So you have to have a transformation matrix over here. So you should know, I mean, it will be, I think, cos theta, sine theta, minus sine theta somewhere. and like that. Okay, so that's where you have to do this transformation of coordinates, and that's how this is written in front of you, which is 4.39. So the same can be applied not just for the positions, but also displacements, velocity, acceleration. Basically any transformation can be done in this form. Okay, so 4.39 is how you would get that using the transformation matrix, and then you can substitute 4.39 into the first of 4.38, which is this one. So you would substitute, for example, dou u by dou x is dou u dash. Okay, so dou u by dou x cos theta plus dou v by dou x sin theta. So you will make those substitutions, and you should eventually arrive at ex dash is equal to ex cos square theta plus ey sin square theta. If you have any doubt about problem 1.2, please ask me. Okay, separately you should definitely ask me. I am not doing this because this transformation you must have done at several places before, but you still have a doubt, please ask me. Please don't just learn up the formula of problem 1.2. You should actually know how to do that transformation. Okay, so ex dash is equal to dou u by dou x cos theta, sorry, ex dash is equal to ex cos square theta plus ey sin square theta plus gamma xy sin theta cos theta. So this is how you would be able to find ex dash. By a similar method you will find ey dash, so you will basically write the expansion of this one. Okay, and then you would substitute equations 4.39 into this, and you would get ey dash, and similarly you will get a gamma x dash y dash by 2. So one of the important things about this is that you can find the the strain in this new transform coordinate system with respect to the old one. Okay, so this is something which you had done similarly in the case of stress, and now you have seen how it can also be done in terms of for the strain. So theta is this rotation which is happening for the coordinate system. Okay, fine. So that sort of takes away the part of rotation of the strain. Okay, so the next topic which we would study is the Mohr's circle representation of plane strain. So buckle up and we will proceed in for this one as well, but this time I think Mohr circle should appear easier just because you have dealt with it once. Okay, but many of the terminologies are same or similar. So when you compare equation 4.41, which is this transformed equation, this was 4.41, okay, with equation 4.25. So let's see what 4.25 was. So 4.25 was about the stresses. Yes, so when you compare 4.41 to 4.25, so this was about the transformation of strain, this was about the transformation of stress. Okay, we see that if in 4.41 we make the substitution E for sigma and gamma by 2 for tau, you will obtain 4.25. Okay, so you make this substitution in 4.41 and you can make this transformation. So if you just look them as equations, you can clearly make these substitutions, because unit wise there will be no problem. The units of the left hand side will be the same as units of the right hand side. So, and that it is easy for us to represent 4.41, which is this equation, as a Mohr circle. Okay, so easy to do that. So you, in the Mohr circle of the strain, which is figure 4.31, the normal strain E are plotted positive to the right over here. Okay, that is plotted to the right or positive to the right, and half the shear strain component, that is gamma by 2, is plotted vertically. So this is gamma by 2. Okay, and this is E. Fine. So the shear term is always up vertically. Now if the shear strain is positive, the point representing the x-axis is plotted at distance gamma by 2 below the e-axis. Okay, so if the shear strain is positive, the point representing the x-axis is plotted at distance gamma by 2 below the e-axis, and the point representing the y-axis at distance gamma by 2 above the e-axis. So this is very similar to what we have seen before in the previous case. Okay, so the x point will be below gamma x by 2 for the positive value of shear strain. And similarly, if gamma is negative, the x-axis point is plotted at distance gamma by 2 above. So this would be over here in one of the examples we have seen for stress. Okay, so this x is over here, that would mean the shear strain over here would be negative. So it's the same analysis which we have. And as in the case of a stress circle, the relative angular positions are the same in the real body and in the Mohr circle, but the angles are doubled in the Mohr circle. So a change of transformation theta somewhere like this over here actually causes this line to change by 2 theta. So this was there in the case of stress as well. This was observed, and we had studied in detail how that had been derived. So here we are not going into those details just because it's a clear repetition. Okay, so that is how you would draw. So x y is your original system, x dash y dash is your transform coordinate system, and in this transform coordinate system you have found the shear stresses. In this transform coordinate system you have found the normal stresses. In this transform coordinate system you should have found the normal stresses as well. Okay, so using this particular circle. Okay, now we note that the sets of axis 1, 2 and DE, so let me just rub out these parts. Axis 1, 2, this is 1, 2 and DE are of special interest. So DE is there. The 1, 2 set is the only set for which the shear strain component is 0. Okay, the 1, 2 set is the only set for which the shear strain component is 0. That's obvious because it's lying on this axis where gamma by 2 is equal to 0. Also, the normal strain components has its maximum and minimum value on these axes. Yeah, so this is the maximum value, this is the minimum value, just like in the previous case, and that's why I think you call this as E1 and this is E2, right? We are using the Roman numerals over here, perhaps I think not to confuse with the stress, but eventually I think we'll mix it up anyways. So that's something which you should be careful about. Okay, the normal strain component has its maximum and minimum values on these axes. These axes are referred to as the principal axis of strain, and the strains E1 and E2 are called the principal strains. The DE set of axes is inclined at 45 degrees to the principal axis of strain. That is obvious, that's why you have a 2 times of 45 degree, which is a 90-degree rotation between them. And this is also called the axis of maximum shear strain. So this gamma max by 2 is over there, and this value will be equal to E1 minus E2 by 2. So the maximum shear stress was also uh, sigma 1 minus sigma 2 by 2. Here as well you have this value. Okay, so okay, now you have an example in your textbook, which is yeah, which is like this. So you have example 4.3. In this example, you have a sheet of metal. It's a sheet, so clearly it's a two-dimensional situation which you are referring to. And we don't say the thin sheet, but a sheet means that it's a two-dimensional system. Okay, like a sheet of paper, for example. So the strain components are related to a set of xy axis, and you have the values of Ex as minus 200 into 10 raised to the power of minus 6. So these are the strain values which you have found out, and use the same procedure as for Mohr circle of stresses, except that tau is replaced by gamma by 2. That factor of 2 you should never forget. You should be able to find the normal stress components in this case. Okay, so you want to now find this you want to find the strain in this new system, which is x dash and y dash. So it is rotated by 30 degrees in the clockwise direction. Okay, so you come to this Mohr circle, and here, just like in the previous case, you have to first figure out how to draw this xy diameter, and that is easy. So your Ex is minus 200. So this is the origin. Okay, so because your Ex is negative, it will go to this point minus 200. Then you have the gamma by 2 as 450, which is positive, and that's why it is a line. So that's how we know that it is actually below the E axis. Okay, so the point X is located like that. Similarly, Ey is positive. Okay, so it will be on the positive side of E, and gamma xy is positive again, and that's why y is lying above the E axis. So xy is located now. Okay, that's the first part, and you have all these coordinates there with you. So clearly you also have this point C as well. Okay, once you do this, now after this you have to take this sort of rotation into the account. So figure 4.33 shows the Mohr circle laid out on the basis of given strains. This point x dash lies at a relative angular position twice the existing in the actual body. That is a position of 60-degree clockwise from x. So you have to rotate this 60 degrees. Okay, so you have done that over here. Okay. Should it be 60 degrees like this? It should go up. So 2 theta over here clearly should be 60 degree, because but the direction of this I'm not really sure. Okay, the position 60 degree clockwise from X on the Mohr circle in a manner similar to the calculations of the stress. So okay, once you have drawn the X dash and Y dash, I don't think there's much problem over there. But my doubt over here is that whether the rotation of 60 degree must happen like this, or it should happen in the clockwise direction. So in the previous case, you would want to rotate it anti-clockwise. Okay. Yeah, the direction is correct. I mean, if you look at the figure over here, 4.31, okay. So this is how this rotation has happened, okay, in the anti-clockwise direction. And this was when the angle 2 theta was positive. In this case, the angle 2 theta is negative. So the arrow, this rotation is in this direction, so this time it must rotate in this direction. Okay, so this is 60 degrees. So if you have found out x dash and y dash, and once you have found out the x dash and y dash, all you have to do is find the radius of this circle. Okay, and you don't have to worry about units because strain doesn't have units. You have seen that in the derivations as well. And similarly, you can easily find what ex dash is. Okay, so this is over here. This is the value of ex dash. Similarly, this is the value of ey dash. Okay, this y dash. Okay, and gamma x dash y dash. So it's easy for us to find out. And once you have all these values, you can find the principal strains as well. All you have to find is this particular thing. So E1 you'll have to find out. So if you arrive, say, until a certain point, and then after that you can add those values separately. Okay, so that's how you would find this. I mean, if you are very enthusiastic about geometry, you can always write the equation of circles and do it mathematically and draw it nicely. One of the important things which you should know is that you must know how to draw these circles. So you should be able to employ a compass and a ruler to draw these circles. Okay, please don't be lazy about it. You will have to use this, so please get them, and you should be able to draw nice Mohr circle and make these transformations in any direction you would want. Okay, for example, in this particular case, this xy will always be the same, right? Once you have known what the strains are in the xy coordinate system, what will change is this x dash and y dash, and that will change according to the angle of your rotation of the axis. So you can keep on drawing as many circles with a pencil over this, okay, depending on what the rotation is in this case, and keep on getting the values of this. So if you, once you become slightly more advanced in this, you can also get into a computer programming and see this geometrically. I mean, equation wise you don't have to worry too much, that is already there for you, okay, like this one. But this geometric and this visual interpretation of the Mohr circle is actually very important. It gives you actually a physical picture when you start seeing problems. It helps you visualize strain better, okay, something which does not come out in the index notations. Okay, so that's where we have this, and we will also briefly discuss this just like we had discussed it for the general state of stress. We would also do this for the general state of strain. Okay, you would again have three circles like this one as it was in the previous case. So we'll just briefly go through this because I mean the definitions and everything are all the same. Basically the maths part is all the same. It is the what is stress and what is strain are very different from each other. Okay, interpreting it in Mohr circle and graphically seems the method is similar, but they are completely different things from the theoretical point of view. Okay, so we have now until now considered displaced deformation in a single plane, I mean plane strain as we called it, and we now consider situation in which the strains associated with the z direction are not zero. Sounds similar? Sounds familiar? Yes. Okay, that is a situation in which the state of strain may be said to be perfectly general. So in this case, suppose you are again interested in the strains associated with a set of axes originally lie in the xy plane. You illustrate this situation in this figure 4.35. So please look at OCDE, okay, and it's an undeformed element of a solid. So there's a big solid and this is one part of it. The reference and the point of interest being O. So OCDE is a small region around it. So this is parallel to the xy plane and is given a general displacement in which the z displacement designated by W. So this can also be compared with the figures of the stress which we have learned before, and the OCDE displaces only in the xy plane. So compare this with 4.29. This one, so OCDE displaces only in the xy plane, so there is no displacement in the z direction. But in this particular case, there is a displacement in the z direction, and that is shown by this W over here. Okay, so W is the displacement. For a general displacement, U, V and W are the components in the x, y and z direction. So O has clearly moved to O dash, and you can see all those values around you. Okay, so in the previous case W was 0. Now in our consideration of the plane strain, the effect of dou v by dou x delta x on the length OC was neglected when the strains were compared when the strains were because the strains were small compared to unity. And then you have plane strain, the effect of length OC. So let's see 4.29. Okay. So if you see OC and the you did not take dou v by dou x into delta x. This was neglected. You took a dou u by dou x into delta x, but you did not take a dou v by dou x into delta x. Okay, and this was the effect of dou v by dou x delta x on the length OC was neglected when the strains were small compared to unity. We see in figure 4.35 that the displacements this and the other one, which will be dou w by dou x into delta x, will play a role in the fashion of in the change in length of O dash C dash. So let's see O dash C dash. You are seeing this term and you are seeing this term, something which was missing earlier on. Okay, so you want to consider them, and that is what is shown in this particular figure. And then that's the first part of it, that for small strains the out of plane displacement W has no effect on Ex or on the normal strain associated with any axis originally lying in the xy plane. To the same degree of approximation, the displacements dou u by dou x into delta x and dou w by dou x into delta x and so on have negligible effects on the angle C dash, O dash and E dash. So this is how you would, I mean the actual derivation is not shown, perhaps because it is very similar to that of the strain, but you will similarly have these three values of principal strains, and this is the rotated system in which 1, 2 and 3 are the principal strain directions. So this is how you would arrive at this part, and sort of one of the last topics which you must self-study, and I can tell you how to self-study. You have to go to YouTube or any other video streaming platform and try to read this section with these keywords. It is given in your book also. photoelasticity, brittle coatings, and strain gauges. Okay, you have to learn about a Wheatstone bridge. You may have learned it in electrical engineering at some point. Okay, so strain gauges, you work on the principle of Wheatstone bridge. So this section is about measurement of strain. Experimentally, if you are given a solid which is deforming, how do you measure strain? And the last thing which is not in your book is something called digital image correlation. You have to be very sure and certain about what these methods are. Okay, they will not be taught to you in this course, but they are definitely be something which you will be evaluated on in all of your evaluation components. So please read this section very carefully, and you should be able to find out what these methods are and how these calculations are done. Okay, so that is where we end this discussion on strains, and in the next class we will discuss the relationship between stress and strain. I have said that the theory of stress is independent of the theory of strain, but it does not mean that any point O which we are concerned with, the stress and the strain are actually related through some relations between them, despite the fact that they are two completely different things. Okay, so we'll meet in the next class and take out from there. Thank you.